Now I want to continue our exploration of the world of proof by induction, and I want to look more specifically at this type of example of a proof by induction question, which is a recurrence relation. Now, a recurrence relation, let's just get what a recurrence relation means, get it out of the way, get it over and done with. A recurrence relation is basically something which defines the next term in a sequence. So you've got a sequence. A recurrence relation is something which defines the next term in terms of the last term. Okay, so say like if you have, let's say 1, 1, 2, 3, 5, 8. Hopefully you should recognise this, or you might recognise this, as something called the Fibonacci sequence. And basically the next term in the sequence is defined as the sum of the previous two terms. So here you've got 2, which is defined as 1 plus 1. Okay? And then the next term is the sum of the previous two terms, so 2 and 1, that makes 3. And the next term, and that's 2 plus 3, which is 5. The next term is 3 plus 5, which is 8, and so on. So the next term would be 5 plus 8, which is 13. Okay, and so on and so on and so on. This is a Fibonacci sequence. So that would be an example of recurrence relation, because the next term is given by the previous terms. Okay, the values of the previous term. So that's all a recurrence relation is. Okay, and I'm just going to talk you through an example of a question. It'll be very typically something like this. You'll be given slightly different information, different numbers basically, but it's going to be, if you can follow this, you can do it in the exam, hopefully, with a little bit of practice. So I'm going to be looking at question 8, part B, of the January 2013 FE1 EdXL paper. And it tells us that a sequence of positive integers is defined by, so this is the information which is given to us. It's given to us for free, if you like. The first term is 1. Okay, so U1, U is the sequence, the little subscript here. This little subscript down here defines the term number. That's all the notation means. Okay, and we've got the first term, so U1 is equal to 1. That's given to us. And here is the recurrence relation. So the next term is given by the previous term plus whatever that previous term number is times 3 times that previous term number plus 1. Okay, so using this we can find, what is the next term. Okay, so proof by induction, here's what we asked to do. We prove by induction that the nth term is given by this formula, n squared times n minus 1 plus 1. And again, we're just dealing with positive integers because that's what proof by induction deals with. So let's remind ourselves of the recipe first. These are exactly the same steps for any type of question. We're just applying them in a slightly different way. Okay, so here we've got the base case. We need to prove it. And in actual fact, in this case, we don't just need to prove it for n equals 1, but we also need to prove it for n equals 2 as well. And let me just explain very quickly why we need to do that. We're given n equals 1. We're given that the first term in the sequence is just 1. We're given that. Okay, so we do need to verify that it works for that one. Okay, that the nth term, when we plug this in, when we plug 1 into this thing in here, we will get 1 out. So we do need to verify that it works for n equals 1. But also, because we've been given this information here, we've been given that the next term is given by the previous term plus this thing here. So we need to verify that this also works for U2. So we work out what U2 is. U2 is a band, I know, but we work out what U2 is. So the second term in the sequence. And then we also need to verify that, so we need to come up with the value of U2 using this, and then we need to verify that this formula also works for U2 as well. Okay, so we need to verify it for these two cases with base case. Normally we just verify it for n equals 1, but because it's a recurrence relation, we're given a recurrence relation in terms of the previous one as well. We need to verify that it works for both of these. So n equals 1 and n equals 2. If it was a recurrence relation as un plus 2, was given by un, it was a function of un and un plus 1. So the previous, so not just un, here we've just got un, which is defined as a recurrence relation, but if it was using un plus 1 as well, so say for example un plus 2, for example, was given by 3 times un plus 6 times un plus 1. Then we need to prove it for not just n equals 1, n equals 2, but also n equals 3 as well, if it was something like this. So basically we just need to prove it. We need to prove the base case for however many we're given. Okay, so here we've got the nth term, the n plus 1th term, and the n plus two term, so we've got three terms in the sequence, so therefore we're going to have to prove it for n equals 1, n equals 2, and n equals 3 as well. So that's kind of a general rule of thumb. However many terms in the sequence you've been given is the number of base cases that you have to prove. Okay, so in this case we've only been given 2, we're given un and un plus 1, so therefore we need to prove it for n equals 1, equals 2. Hopefully that makes sense. Second step, assume some general case is true, which in this case is n equals k. And then we need to show that it worked. Then we need to show that the next general case, n equals k plus 1, depends on this previous case. Same thing as before. And then the final step is just the conclusion, saying the right things in the right order. So let's just jump in and let's try and do this. So the information we've been told that u1, first term in the sequence, equals 1. And we've been told that the n plus 1th term is given by the nth term plus n times 3n plus 1. And we've been told to prove that the nth term is given by this formula, n squared times n minus 1 plus 1. So let's do the base case first. Again, write these steps down. The examiner can then follow exactly what you're doing. So prove it for the base case. So let's first of all, remember we need to prove it for n equals 1 and n equals 2 as well. So first of all, we've been told that when n equals 1, so u1, the first term in the sequence, equals 1. And we need to basically we need to verify that this formula here does work for u1 equals 1. Okay, so u1 equals 1. So u1 is equal to, we've got 1 squared times 1 minus 1 plus 1. Well, that's going to be 1 times 0, which is going to be, and then plus 1, which is going to be 1, isn't it? So it does work for u1 equals 1. Now we need to also verify it works for u2. We don't know what u2 is at the moment. So we need to work it out using this formula here. This is the formula to work it out. We've been told that this is true. So we need to work out what u2 is, do a little bit of work. So it's going to be given by u2, u1 plus 1. I'm going to actually write u2 as u1 plus 1 first. Okay? Because then you can see that n equals 1. Okay? So u1 plus 1, that's going to be the same as u2. It's going to be given by u. Remember, n is 1 in this case. So 1 plus 1 times 3 times 1 plus 1. Okay, and we know that u1 is equal to 1. So it's going to be 1 plus 3 times 1 plus 4. 3 times 1 plus 1, sorry, is 4 times 1 is 4. So 1 plus 4, which of course is going to be equal to 5. Okay, so we know now that u2 equals 5. And then we need to verify that this formula here does work for u2. So it does equal 5. So u2 is equal to 2 squared times 2 minus 1 plus 1. Okay, that's going to be equal to 4 times 3 plus 1. So, sorry, not 4 times 3, I've added those two. 4 times 1, 2 minus 1 is 1, plus 1, that's going to be equal to 5. So, therefore, it works. We've shown that the base case is true for n equals 1 and n equals 2. Okay? So we've shown that the base case works. Quite a lot of work there, but you know, hopefully you can follow what I've done. Basically, we need to prove it for both n equals 1 and n equals 2. Now, our next step is our assumption step. So we need to work out what expression for the general case is. So in other words, n equals k. Okay, and we assume uk is true. Okay, so what is UK? We use this formula that we've been given. We want to verify formula we want to verify. So it's going to be this formula here. This is the one which we want to use. It's the one we want to prove. So UK is going to be equal to k squared times k minus 1 plus 1. Okay, and we assume that that is true. Now our next step is our inductive step. And we want to try and link that inductive step back to our n equals k. So our inductive step is testing n equals k plus 1. So let's try and come up with a formula for n equals k plus 1. So uk plus 1, so n now is k plus 1, is going to be given by, well, it's going to be given by looking back at our original formula, which is un is equal to n squared times n minus 1 plus 1. Okay. So our uk plus 1 is going to be given by k plus 1 all squared, that's our n, times n minus 1, which is going to be k plus 1 minus 1. Remember, use brackets. Be careful here. Use brackets if you're not sure. Plus 1, which of course is going to make that equal to k plus 1 all squared times it's going to be k plus 1. I'm just going to write that a little bit neater just by writing this k at the front instead of at behind, because in my mind that just makes it look a little bit neater. But we've also got another formula for uk plus 1, haven't we? If you look at the original thing we were given a formula for uk plus 1, so our n plus 1th term, in terms of our last term, our nth term. So we know now that uk plus 1 is going to be equal to uk, just replacing n with k, plus k times 3k plus 1. So we've got uk plus 1 is going to be equal to, let me just write that down again, uk plus k times 3k plus 1. Well, we know what uk is equal to because we worked up here. We assume that this is true, that this works. So we can now simply just replace uk in our inductive step with this thing up here. Okay, so let's do that. So we've got uk is going to be equal to k squared times k minus 1 plus 1 plus this thing on the end as well. So plus k times 3k plus 1. So what we now want to do is verify that this thing here, is equal to this thing here. Okay, so we want to show that k times k plus 1 all squared plus 1 is going to be equal to this thing, which is k squared times k minus 1 plus 1 plus k times 3k plus 1. A lot of algebra, but where do we start? Do we start with this side and try and turn it into this side, or do we start with this side and try and turn it into this side? Well, remember my rule. With algebra, you always start with the side that's not being compressed. This side has got less terms, so it's compressed. Okay, it's been made smaller. Whereas this term's got more terms, so it hasn't been compressed yet, and means that we can do the compression. Okay, so here we're going to have to add terms. We're going to have to basically rely on guesswork to turn it into this side, whereas this side we can just compress terms quite nicely. Okay, so follow our nose. I'm going to write this side then again down here. I'm going to do my working down here, and I want to turn this side into k times k plus 1 all squared plus 1. Okay, let's do it. So first of all, the first thing which I'm going to look at is these brackets. I want to get rid of these brackets. Okay, I will need a bracket later on, but I can put that back in a later date. The brackets are stopping me. It's kind of like a barrier in my mind. I want to expand these brackets out, then collect together those terms. So k squared times k minus 1. So I'll end up with k times k squared times k, which is going to be k cubed. And then I'm going to multiply this k squared times this minus 1, so I'm going to end up with minus k squared. I'm going to have this plus 1 still. Then I'm going to multiply this k over this bracket here, distribute this k over this bracket here. So I'm going to end up with 3k squared, okay, plus k. Okay, now the brackets are gone, I can collect together those like terms. So, and I'm also going to write it in decreasing powers. Okay, so I'm going to start with the highest power, which is k cubed, which I can see. I can see here I've got a minus k squared, but I've also got a plus 3k squared here. So I'm doing minus 1 of something, plus 3 of something. So I'm going to end up with 2 of that something. And in this case, that something is k squared. So I'm going to end up with 2k squared. Okay, and then I'm going to write the next highest power, which is going to be k. Then I'm going to write the plus 1 at the end here. Right, okay. Now at the moment that's a cubic, which can be quite difficult to expand, to factorise. But remember what I'm after here. I'm after k times k plus 1 all squared plus 1. So in my final answer, I've got this plus 1 sticking around at the end. Okay? So I can leave that plus 1 alone. I can almost ignore that plus 1, pretend it's not there for the moment. Okay? And so basically I just need to concentrate on this first bit, this bit here, and turn it into this k times k plus 1 all squared. Okay, well first thing which I want to do is I want to factor out a k, because there's k multiplying out the front. So let's factorise out a k of this thing, this square bracket here. So I'm going to be left with k squared plus 2k plus 1. Okay, and I've still got my plus 1 at the end. And then I want to basically verify that this bracket inside these curved brackets is indeed k plus 1 all squared. So I'm looking for two things that multiply together to make 1, and two things which add together to make 2. And that's going to be 1, isn't it? So it's going to be k plus 1 times k plus 1, which is just, I can just write as k plus 1 squared. Okay, you can verify by multiplying that out that is that if you're not sure. But it is that, trust me. And then you've got a plus 1 at the end. So now I've basically shown that this side here is indeed equal to this side here. So therefore I've shown that if k is true, then k plus 1 must automatically be true. So my conclusion then, just writing the right things in the right order. I've done the algebra, done all the hard parts. The conclusion, I've said that basically uk plus 1 is true, so n equals k plus 1 is true, is fine. So uk plus 1 is true, I'm just writing in terms of sequence notation, is true if the previous term, uk, is true, because it depends on that. Remember, we depend on uk being true to get to this answer, because we use that in our algebra up here. So we basically said that uk plus 1 is true if uk is true. And since u1 and u2 is true, then it is true. We have shown by induction, you could write, but I'm just going to write it is true for all n, which is a member of the positive integers. Okay. There we are, simple as that. Okay, hopefully that makes sense. In your exam, the hardest thing which you've got to remember is, the biggest question that you should be putting out here is, how many base cases do I have to show with the recurrence relation? With all other types of induction examples, just show it for one. For n equals 1. Okay? But for the base case of recurrence relations, you think, how many examples do I have to show? Remember my general rule. You look at this thing here. Okay, the thing which you're given, the formula which you're given. Okay, and you look how many terms your formula uses. So how many terms your formula uses. So in this case, it's 2 terms. You're using un and un plus 1. Right? So therefore, you're going to have to prove it for 2 base cases. u equals 1, and n equals 1, n equals 2. Okay, so u1, u2. If it was something like, as I say, let's say un plus 3. Un plus 2 would be using 3. Un plus 3 will be given as, if it's given as something like 3un plus 1 plus 6un minus un plus 2. Then you'd have to prove it for 1. Then how many terms have we got? We've got 1, 2. I think that's just gone slightly off the screen, but that's un plus 2. 1, 2, 3, 4. So you'd have to use it for n equals 1, n equals 2, and n equals 3, and n equals 4. Okay, so that's basically the general rule which you have to do. Hopefully that makes a little bit of sense.